Well, hello everyone, this is us doing our final video lecture on Chapter 4, Linear Regression. And here we're going to deal with what's sometimes called linear wisdom or regression wisdom. We're looking at linear regression issues, things that you have to be aware of, and how you get around some of the problems and situations that can occur when you're trying to do linear regression. And as you can see here, the five main themes. What does residual plot tell you about your linear regression? The concept that correlation is not the same as causation. The dangers of doing what's called extrapolation. The effects of outliers. And finally, problems and general problems that you can get with linear regression. So first thing we're going to look at is what does a residual plot tell you? Well, when we do linear regression, we have our scatter plot, say this on the left, and our brain is kind of hardwired to see patterns, and so we sometimes look at data and sometimes you might see a curve and sometimes you might see a straight line. It's kind of how your brain is working, but judgment calls such as that are not a good idea. So what you do is you do the residuals. So you imagine the best fitting line and you plot how far away they are. So this is the X, and up here it's the residuals. Now what you want to see is a whole sequence of dots above and below the middle line at 0. Now this isn't that way. It's good on the left, it's reasonably good on the right, but you see in this middle part there's none above and they're all below. That is an indication that your data is not linear, and therefore it would be a bad idea to use linear regression on it. And the residuals allow us to not be persuaded or influenced by our observation that our brain looks at the data and says, yeah, it looks linear to me, when it's not as linear as you think it is. Now this one here is a big issue in all linear regression questions. And it says correlation is not causation. So what we're saying here is you've got your scatter plot, your X's and your Y's, and the data looks really linear, and then you make the big jump. That means that X is causing Y. That isn't what a good linear correlation model is telling you. What it's really telling you is that X is a good predictor of what the value of Y is going to be. It's not the same as causing it. The reason behind that is that there might be another variable. It's called a lurking variable. It's a hidden variable that's the real cause of what you're seeing. So let me put that idea across by giving you two simple examples. They're kind of silly, but they do emphasize the issue here. So what we've got here are some 20 young students, right? Let's say from 5 to 15-year-old. And you've measured their shoe size, and then you've done a standard reading age test. So typically a 7-year-old would be reading at a 7-year-old level, but some 7-year-olds are reading at an 8-year-old level, some are reading at a 10, some are reading at a 5 or a 6. So you've got the shoe size and what they tested as a reading age, and it's really good data. I mean, look, that's pretty linear. It's got a nice high R value. Its R squared is about 82, 81%. Very good fit. Nothing wrong with it. And then you make the big assumption. Well, X is the shoe size, Y is the reading age, so that must mean that your shoe size is what's causing your reading age. Well, if you think about that, that doesn't make sense. The size of your feet makes you a better reader. So people with big feet would be able to read at a higher reading age than people with small feet. Why that should even be the case makes no sense. Can you imagine a really weird country where they wanted to increase the reading age of their children? Well, what they would do is they'd have this special operation where they'd break their feet and stretch them out 4 more inches. And then the next day after the operation, according to this model at least, if shoe size was directly involved in your reading age, they'd suddenly be able to read better. Well, we know that's not the case. So what is happening here is that you're seeing a relationship not between shoe size and reading age, but between the age of a child and his reading age. And that really should make sense, right? A 9-year-old should read roughly about a 9-year-old, give or take. So what's happening? Well, children, as they get bigger, their feet get bigger. And so isn't your shoe size very closely connected to the age of the child? So all the shoe size is really doing is indirectly measuring the age. And it's the age of a child that's the main cause for the reading age. Now, that makes much more sense than just saying it's the size of your feet. So be aware that just because you have got a good linear regression model, you cannot make the assumption that that is proof that X is causing Y. There could be this third lurking variable that's connected to X that's doing this. So what we have here is a chart that represents average life expectancy and the number of televisions in the household. So can you imagine a country that had, I'm pretty sure there should be a decimal point here, 6 televisions per household, or 9, and I guess you have to decide what's the television. So in today's world, the television would be televisions, cell phones, computer monitors, laptops, tablets, and so on. So you could imagine they could have 7.5 roughly, or 9, or 6. What this data is showing us is quite clearly linear. There are a few kinks, but a good linear fit. Its R value is about 0.7, so it's not great, but it is a connection. And you might say, wrongly, the more TVs and devices like televisions that a household has in a country, the longer those people live. So that must mean having lots of TVs makes you live longer. Well, you know, that's stupid, right? That's not sensible. So what is happening here is that there's a lurking variable. And the lurking variable on the number of TVs a household is connected to the wealth of that country. If you're in a rich country, you will have lots of cell phones and televisions and monitors and tablets and who knows what else, right, in your house. If you're a poor country, you'll have very few of those. So what you're really measuring along the x-axis is the wealth of a country. Richer countries people in those countries do tend to live longer. They have better food, more food, good medical, preventative care, treatment after care, the whole 9 yards. A poorer country, poor food, poor quality of food, not enough food, very poor infrastructure as far as medicine goes. Access to preventative care and treatment is a lot less. Those poor people tend to, in those countries, have a lower life expectancy. So, correlation, good straight line, does not mean X causes Y. It could just mean that there's another variable connected to X, the lurking variable, that is the real connection. It doesn't mean you can't use your scatter plot, because X is still going to be a good predictor of Y. Right? It'll predict the value of Y. It's just not causing the value of Y. Now, the next one is called the dangers of extrapolation. If you've got a good linear model, suppose this one is predicting the weight of children, and it's 30 plus 8 times their age. What would a 50-year-old be? Well, this is the danger. If you try and use this model on someone who is not in the range at which the data was collected. This data was collected for teenagers, right, 5 up to 15. If you plug a 50-year-old in here, you are going to get the ridiculous answer that a typical average 50-year-old, according to this model, would weigh 430 pounds. Whenever you try and use, for the X value, in this case age, a number that's not in the range in which the data was collected, we call this extrapolation. And it's very dangerous because you're making a big assumption that the data continues to be linear after, in this case, 15 years. Well, I can pretty much predict that that's wrong. Don't you get to about 18, 19, then it'll plateau in some way. So you're not allowed to, or you should be at least very careful about using your model to predict it beyond the range in which the data was collected. So what about this then? What do outliers do to your model? How do they affect it? Well, they can affect it in two different ways. They can affect it by changing the value of R squared, right? The correlation, the coefficient of determinant. It can affect it by making it larger than it really truly is, or smaller than it truly is. And then secondly, it can have the effect that it is changing the equation of the line of best fit in some significant way. What we have here are some examples of some linear regression lines with one outlier. So you can imagine this is the main mass of the data, and then you've got one outlier here. Now in this case, the outlier has the feature that it's in the general direction of the data. Now if you were putting the best fitting straight line through that, the data, the straight line would be the same with all the data, or if you took the outlier out, right? It would look just the same straight line, give or take. But what would happen, what would change would be the R value, or the R squared value. This guy here does a lot of damage. It does damage by making you think that your fit is much better than it is. I'll show you what that looks like. Here we go. Now, when that outlier was included, the R squared came out at 80%, and this is the equation of the straight line. If you then removed that one data point and recalculated it, the R squared is now 60%, but the equation of the straight line never moved at all. That particular type of outlier is going to have the effect of making the R squared bigger than it truly is. It's a little bit difficult to explain why it's doing that, but essentially it's like a Bill Gates, you know. Bill Gates makes the mean much bigger than it really is, right? The Bill Gates effect also makes R squared, in this particular world at least, much bigger. So we have to be aware that outliers can make us think our model is better than it truly is. Now what about an outlier that's, say, away down here? Well, if you have this guy, he will affect the R squared if you remove it. It's going to be bigger, a lot bigger. And the equation of the line is also changed. Instead of going this way, which is what it would do if you didn't have it, it's going to get bent a little bit towards it. So you can see that the slope changes a little bit between the before and after. So outliers do have an effect. It depends on where the outlier is, what that effect is. So to finish with, let's look at problems with linear regression. You can, for instance, have data that looks like this. If ever you get data that consists of two distinct groups of data points, then what you're probably looking at is not one homogeneous data set, but two separate groups. The kind of groups that you might get are males are one set of dots and the females are the other. It could be that one set of dots are people who are healthy and the other set of dots are the values for people who are unhealthy. And that's kind of helpful, you know, kind of useful to know. But if you want to do a model of it, what you have to do here is you have to split the data into two separate groups, typically, and get the linear regression for each. And then if you're a male, you use this formula to model. If you're a female, you use this one. They sometimes do that with all sorts of things. For instance, if you're going to do a child's age against weight, you should really separate them into boys and girls because they grow at different rates and the data is much more accurate if you compare a boy with the typical distribution of what boys have weight-wise with age as opposed to doing it with a girl. And so, separate scatter plots. And lastly, well, if it's not linear, don't try and make it linear. Give up on linear and move on to some other regression. quadratic regression, exponential, cubic, logarithmic, to name but a few. The name at the front, quadratic for instance, says that you're going to fit the best fitting quadratic through the data, or exponential function, or logarithmic function, or cubic function. All are valid, but better fits to your data. So that is me finished. Thank you for listening.